Hello everyone, it's my pleasure to present our paper about robot calligraphy there. The first thing I want to say is robot calligraphy is a hard but interesting task. The calligraphy itself is a kind of beautiful art form. It is pursued by many people for several thousands of years. However, it is also very difficult to learn because generally it takes human many years of practice to really master this kind of art form. The main difficulty lies at the writing brushes. It has a soft tip with some highly nonlinear properties. And so making robot be able to write calligraphy would be a great contribution for human's daily life. It would also be great for the big area of robot art and also the soft robotics area. Current work in this area focus on either a learning-based method or a trajectory optimization-based method. As far as we know, learning-based method is still not very mature for now. In this paper, we are mainly considering the trajectory optimization method. Such method generally requires a good knowledge about the writing brushes. And so, however, the current proposed brush models are either too complicated or either too simple to generate some very good results. And so in this paper, our main contribution is proposing a novel virtual brush model, which is both accurate and runs very fast. We also propose an efficient optimization framework so that it can generate very good writing trajectories for the robot to execute with. Here is the methodology flowchart. The input could be any character Unicode, and then our optimization program will take it and find some optimal trajectory corresponding to it. The robot will take these trajectories and execute it with the writing brushes, and finally we will get the written results. We will look at the optimization process mainly has two components, the virtual brush model and the trajectory optimization part. We will look at the model and first. The virtual brush model also has two components, the drawing component and the dynamic component. Basically, in the drawing component, we want to map a set of brush parameters to a writing mark in the paper. The brush parameters include, at first, the end effector coordinates, which describes the position of the virtual brush, and then an orientation parameter, which describes the rendered writing mark on the paper. Width and drag parameters describe the shape and the size of the writing mark. And finally, offset describes the relative distance between the writing mark and the brush holder. We also would like to introduce the concept of root point, just as this yellow dot shown in the brush model. The position of the root point can be calculated from some geometric relationships. At first, we can project the end effector coordinates to the paper plane, and then we will move the projected point following the direction specified by the orientation parameter for a distance specified by the offset parameter. There are two things worth of notice there. At first, offset is simply the horizontal distance between the root point and the end effector coordinates. And also orientation can be gotten if all the other variables are known in this definition formula of the root point. And so then we will look at the dynamic component of the virtual brush model. The control signal is represented by U, which is the velocity control signal of the end effector. The end effector always holds the brush holder. And then the brush state parameters are updated based on the current state parameters and the current control signal. We'll take a further look at this nonlinear function f there. The end effector coordinates are simply updated based on the velocity signals. The width and drag parameters are updated in a more complicated way. We performed a lot of experiments to connect the writing marks at different situations, and here is what we find out. In these two figures, it is shown that the width and drag parameters follow a very good linear relationship with respect to the z parameters, which describes the how much the brush is pushed down during the writing process. And so we run a linear regression there, and then it gives us the width and drag function in the updating formulas. During the real writing experience, we found that the real updating of the width and drag parameters are pretty smooth. And so we also further introduce an inertia factor like the KW and KD in these updating formulas to model this phenomenon. Before introducing the updating formulas for offset and orientation, we want to show the writing record at first. In this record, it is shown that although the brush holder is always moving, the tip does not always follow the movement of the brush holder, especially when the brush is pushed down and when the brush is making a turn. We think there are mainly three reasons. At first, we know that the tip of the brush is soft, and so there's some elasticity. And also during the writing process, there is a friction and surface tension generated between the brush and the paper, and this force will have a tendency to stop the tip of the brush from moving. As such, only after the brush holder is far away enough from the tip of the brush, then will the tip of the brush will move. Otherwise, the tip will stay at the original position because of the influence of friction and surface tension. This important observation gives us the updating formula for the offset and orientation parameters. In the first formula, the first offset function describes the maximum possible offset parameter at each time instance. And the second offset function describes the horizontal distance between the root point and the end effector coordinates. The logic is explained as follows. When the brush holder moves to a new position, we will measure the distance between the old root point and the new brush holder. If this distance is smaller than the maximum possible offset, we assume that the friction and surface tension play the dominant role, and so the tip will keep still. However, if this distance is larger than the maximum possible offset, then the tip must have moved. However, under the influence of friction and surface tension, the tip will try to move as little as possible. And so in that case, the new offset parameters will be set as the maximum possible offset parameter. And the updated root point will stay at the line between the old root point and the new end effector coordinates to minimize the moving distance. And so now we are able to update both the root point position and the offset parameter. We can uniquely solve for the orientation parameters from the definition formulas of the root point. Finally, the maximum possible offset is also measured from the watermark experiments that we use to derive the updating formulas for the width and drag functions. After introducing the virtual brush model, we will look at the trajectory optimization part. The basic idea is inspired from pseudo-spectral optimal control. Basically, PS method uses convocation points to parameterize the trajectories. After specifying a set of convocation points, the original trajectory can be reconstructed by Lagrange polynomials. This is a very efficient method to parameterize strokes, and just like this simple figure example shows, it could provide a very smooth and accurate approximation with very few parameters, and it can be run very efficiently even at the higher order situations. And in this project, we are using this pseudo-spectral method to parameterize the stroke trajectories. Also, during the optimization process, to make the optimization run more efficiently, we extract the individual strokes from the original character image. Stroke extraction is about extracting the small strokes from the original character images. There are many algorithms proposed from the image processing aspect. However, most of them are complicated and requires a lot of calculation cost. In our case, we propose to use vector graphics pictures as the reference pictures, which provide very fast and convenient stroke extraction. As for stroke trajectory parameterization, since there are three components in the three-dimensional space, we will also use three sets of parameters corresponding to the x, y, and z axes to parameterize an individual stroke. Here is our optimization objective function. Basically, we want to find a set of stroke parameters which could minimize the picture difference between the reference picture and the simulation picture. Obviously, the simulation picture is generated by the virtual brush model we just mentioned. We also introduced an recognition term to the objective function to help the optimization process. This whole nonlinear optimization problem can be easily solved via Levenberg-Makruda algorithm. As for the initialization, the x and y components of stroke trajectories are initialized at the middle line of each stroke, and the z component is simply set as a constant value for convenience. This initialization, we also want to mention that this initialization is not enough to generate good results. This figure C shows the simulation results. The red lines are the initial trajectory and the black part are the simulation pictures. We can see that even in simulation, it is not able to generate some beautiful characters. Besides, we also design a program to deep ink. There are two reasons for it. At first, we need to supply ink to the brush so that it can write something down on the paper. Another reason is that we also hope to avoid the simulation error accumulate during the writing process. When the brush is dipped with ink, the brush state will also be restored to a predictable state in our program. This video shows how does the deep ink works. Now here is our final results. Column A shows the reference pictures, and the other columns shows the comparison before and after optimization. B and C shows the stroke trajectories. D and E shows the simulation pictures, and F and G shows the final writing results. We can see the improvement after optimization more obviously from these pictures, where we visualize the distribution of the errors. B and C are simulation, and D and E are the final writing results. We can see the obvious improvements from these pictures. We also record a writing video to basically show our robot configuration.